that the first speaker is Meir Shimon, Professor Meir Shimon, who has a PhD in astrophysics, which, by the way, was something when we were children, when I was a child growing up in the Northeast of the United States, was my dream. I wanted to be an astrophysicist. Everyone who was a nerd, who was into science, wanted to be an astrophysicist because it was the one thing we could never understand. And so we always aspire for that which we don't understand. So astrophysics from Tel Aviv University. Professor Shimon's master's thesis was on 2+1 dimensional gravity. And his PhD dissertation was about physical processes in galaxy clusters. I think we heard Professor Pines talk about Professor Stephen Hawking. And I remember in high school, one of the books that Professor Hawking wrote about gravity was the only way I was able to understand gravity. It was beautiful. So I look forward to Professor Shimon's discussion to us. So Professor Shimon, please, the floor is yours.
Thank you, Lucian, for the introduction. I also wanted to thank everybody for coming, and especially to Ephraim that invited me to give this talk, from which another talk emerged, the idea to talk about the Boltzmann brain. Yes, so let me just see if I can share the slides with you. Just a second. So do you see it? Okay, let me just in the view mode. Okay. Okay, so the anthropic principle has to do with the word anthropos, a man, person, but actually doesn't have necessarily to do with that. I mean, this is the way that it was first presented, but we're talking about any carbon-based life form, right? So, so let me start with a quote by Albert Einstein. He said, "What really interests me is whether God had any choice in the creation of the world." Right? So, of course, we physicists try to see how things work, but a deeper question is, could they work differently? I mean, it's not, I mean, for us at least, it's not enough to see how things work. We would like to see the foundations of the physics. How, I mean, what freedom did God, creator, whatever you want to call it, had in creating our world? So what are laws of physics? Laws of physics are just equations, constraints on physical quantities, how they behave, how they interact with each other. This is a famous equation that everybody knows. E equals mc squared. E is the energy, m is a mass, and c is the speed of light. So c is a constant of nature that is used just in conversion of units from mass to energy. So energy and mass have different units, and c is just a conversion factor that has units of speed of light, and it's a mediator between mass and energy. Another example is Maxwell equations. This is a set of 4 equations that govern the dynamics of the electromagnetic field. So here on the left-hand side, you see E and B. Here E is electric field and B is the magnetic field. And the funny symbols here on the left-hand side, these inverted triangles just describe some spatial variations of these fields. And here on the right-hand side, you see here the letters T, here and here. This just a symbol for the variation of these fields with respect to time. Again, to convert from length units, from spatial units to time units, you have to introduce this c, the speed of light. So again, we see c as a conversion factor between different units. We measure mass with a scale, with balance. We measure time with a clock. We measure length with a yardstick. and you have to convert between these different quantities, inherently different quantities that you measure with different measuring devices. Unlike in mathematics, where everything is pure numbers. In physics, we do have to, physics is a science of measurement, right? So here is another example. This is a Schrödinger equation. This is the most famous equation in quantum mechanics. Just ignore the details. The point here is that the left-hand side tells you something about energy. The right-hand side tells you something about frequency. And the conversion factor between frequency and energy is h bar. This is a funny symbol. H is just a constant of nature. And here, this is my last example of physical laws. These are Einstein equations. Einstein equations govern the interaction between, let's say, space and matter, how matter curves space and vice versa. So the left-hand side here has to do with the geometry of space and time, and the right-hand side here, this T mu nu, is the energy density and pressure, things that have to do with matter. How do you go from energy density, from energy, to curvature, to geometry, by just introducing this conversion factor? G here is the strength of gravity, and C again is the speed of light. So we are talking about nature's constants. Here we see a table of nature's constants: C, G, H, the electric field, the electron mass, and the list goes on and on and on. The idea is that these conversion factors, these constants of nature, are universal constants, and you can use them here or everywhere else in the universe in order to convert between units that you need for your physical laws, for your equations. So is there a fine-tuning of nature constants? Are they somehow orchestrated to be consistent with the existence of life, of carbon-based life? So the existence of sustainable carbon-based life is very sensitive to the empirical values of these universal physical constants. This is something that has been known for, I think, at least 50, 60 years. These constants are on a knife edge in the sense that even a slight deviation of one of them would result in no life. Now, I should say that recent studies show that, yes, each one of them, life is sensitive to each one of them, of a set of parameters, not all these constants of nature, but subset of them. But if you vary two of them, so simultaneously, you can still have a large deviation, large departure from the actual values and still have life. But if you do that only for one of them, then you can say that they are on a knife edge in a certain sense that I will define later. Again, these are only the recent studies from the last year, so I cannot say that this is acceptable, an acceptable result on the community, but many of us will agree that if you vary at least one of them from their measured empirical values, then you will end up with no life at all. The universe seems to be conducive to the existence of life as we know it, and this led people to formulate the Anthropic principle, and there are two versions. Actually, there are about 30 versions, but the two main versions are the weak and strong version. So the weak version tells us that nature's constant must be compatible with the existence of carbon-based life, since the existence of life is a fact, right? So this is a fact, you cannot ignore it. This is a point in your data set, just a consistency check. You would like to see that our existence or animal existence or whatever, any form of life is consistent with a constant of nature. The strong version tells us that nature's constant must be compatible with the existence of carbon-based life, since the existence of life is its ultimate purpose. So here we are talking about purpose, about intention, about a plan, and this is something that that many of us find hard to accept, because you need some external agent that has some purpose in creating this world, and this is something that is hard to accept for many of the physicists at least. So here is the first example that I would like to give of this anthropic principle. So we take it for granted that we have one time dimension and three spatial dimensions. We live in a space-time. But actually, if you just look at your possibilities, so here we see this axis, you can see the number of time dimensions, and here in the horizontal axis, you see the number of space dimensions, and we are here in this square, three space dimension and one time dimension. If you try to explore the other possibilities, you hit either kind of instabilities like the tachyonic instability or this portion of this diagram, or the universe will be unpredictable. Just give an example, if we had only one additional spatial dimension, if we had lived in 4 space dimensions and one time dimension, the trajectory of planetary system will be unstable. So you won't have any stable climate. Life would not exist. If you lower the number of spatial dimensions or increase the number of time dimensions, then the universe is too simple to maintain life. So we find ourselves stuck in this square, and this might be a coincidence or might not be a coincidence. Another example is the strength of gravity. You remember the constant G that I mentioned earlier in the context of Einstein equations. If the strength of gravity G is higher than is actually measured, then Earth will be closer to Sun because the Sun will attract Earth much stronger, and this will result in an uninhabitable planet. The temperature on Earth will be too high for life to exist. On the other hand, if G is lower, then the matter that clustered these small perturbations of matter density at the very early universe that ultimately clustered into galaxies and eventually to stars like our sun and subsequently to planets, wouldn't take place or would be much slower, and then life of our kind will not be able to form. So you see that G, the tolerance in variation of G cannot be too large. Otherwise, it will be inconsistent with the existence of our life. Another example is the sun. So I think that I'm running out of time. Let me just do that very quickly. For the star to exist, there is a balance between gravity that tries to collapse all the matter into a single point, because gravity is attractive and attraction force, but in order to keep it stable, you need a pressure, an outgoing pressure, in order to counteract the gravitational interaction, and this is provided by nuclear fusion here at the center, at the core of the sun. So this is a competition between gravitational interaction and nuclear interaction, and here is an example of how things work. For two protons to interact with each other in a nuclear interaction, they have to get over their electromagnetic repulsion because they have the same charge, right? Both of them are positively charged. So they have to cross what is called the Coulomb barrier. So this means that if I increase the strength of electromagnetic interaction, they will have to cross a larger barrier. They won't be able to do that, obviously, and there will be no nuclear interaction in this regime. And this means that there is no counteracting pressure to balance gravity. You will have no stars, no sun, and obviously no life on Earth. If you lower the potential barrier by just weakening the electromagnetic interaction, then this interaction, strong nuclear interaction will be too fast. The star, the sun, our sun, will consume all its nuclear fuel very, very quickly, and it will end its life very, very fast, and life won't have a chance to form because astrobiologists say that we need at least 1 billion years for life to form on Earth. And there are a few other examples. I'll skip them. I'll just say that there is the look elsewhere effect. When you want to say that you discovered something, it's not enough to say that, okay, I found some some remarkable results, something that cannot be explained by some coincidence. You really have to look elsewhere and see what are the other possibilities in order to compare the significance of your discovery to other possibilities. For example, there are many other constants of nature to which the existence of life is virtually insensitive. For example, the quark masses and the Higgs masses. So it's not enough to say that, yes, it's very sensitive to G, to the strength of gravity and electromagnetic interaction. You can compare your requirements to other constants of nature and see that life is insensitive to these other constants of nature. So this means that things are not, not unequivocal. You cannot say that, yes, we have a proof that life cannot exist without changing all the parameters. There are parameters to which life is insensitive. Now, how improbable our universe is. In order to do that, you really have to compare to other universes, but the problem is that we don't have other universes. There are models of the very early universe, like a cosmic inflation and superstring theory, that tells us that there are other universes, actually infinitely many universes, with which we cannot interact. We don't know their properties. We cannot really do a meaningful statistical comparison with them. So these are just artistic impressions of these kind of other universes. Another question that comes here is the Anthropic principle predictive at all? For a scientific paradigm to be accepted, you want your theory to be predictive. So Fred Hall, the British physicist, made some prediction that has eventually been actually measured by experiment and proved to be correct. So this is perhaps the most known prediction made by a physicist based on the Anthropic principle. I don't have time to cover it. This is Steven Weinberg, the American physicist, that made actually an Anthropic prediction for the upper bound of the dark energy, the species of the energy density that causes the universe to expand rapidly, actually accelerate its expansion rate. So he set an upper bound that has been consistent with measurements that have been subsequently made using supernovae. And this is Yakov Zeldovich, the Soviet physicist that used also Anthropic considerations in cosmology. Let me just quickly summarize. Life, as we know it, is very sensitive to the empirical values of certain constants of nature. A few percent lower or higher values, we are talking about few percent, of these parameters will result in an uninhabitable universe. Is it a coincidence? Could it be different? This is a question that Einstein asked. Is it really a knife edge precision? Maybe 2 or 3% is not knife edge, right? How do you know? You don't have other universes to compare with. Is it scientific? Does it make any predictions, right? Is there a purpose? This is a weak versus the strong versions of the Anthropic principle. I mentioned also the look elsewhere effect. We only have a single universe. We have nothing to compare with. Life seems to be insensitive to the precise values of certain other constants of nature, like the quark masses, the neutrino mass, the Higgs mass that I mentioned. So I'll end here and I'm ready to take a few questions. Thank you.
Thank you, Professor Shimon. It was a great presentation. I got really inspired by it. I have my own question, but I'll open it up first to our audience. Yes, I think Professor Ephraim Eliav, do you have a question?
Yes, thank you, Meir, for really very interesting presentation. You have skipped the prediction of Fred Hoyle. I had never heard about this kind of prediction. Could you please say a few words about this?
Sure. So Fred Hoyle is actually famous for another thing that he made. He is the father of the steady state universe, the rival model of the Big Bang. Eventually, we now think that the universe is expanding from the Big Bang. But anyway, he made a prediction. He said that for life to exist, the carbon atom needs some resonance level that was not known at his time. I think it was in the 50s something, 53 or something. And a few years later, it was actually confirmed by experiment. I've read something that was written by an historian of science that said that actually Fred Hoyle, there is no evidence that Fred Hoyle used anthropic consideration, and only in retrospective he ascribed that to anthropic consideration. So maybe it wasn't really a prediction, I don't know. But I think that most of the people would agree that this is a prediction that Fred Hoyle made. Mm-hmm. Other questions?
Thank you, professors. We have no questions right now from social media. So